Hello everyone. So in this video, I will discuss different types of procedural block in details. So let's begin with the generic one, that is always block. So the always block is a generic block from Verilog which does not enforce designer's intent, which could be a problem during simulation because there will be a mismatch between simulation and synthesis. So allow me to demonstrate this with the help of an example. So for this example, I will be writing a very simple module of mux that will have an output y, to input b, and a select line. So I will mention the direction of each signal, and we have two input of single bit each and one select line. So since there are two inputs, the select line should be of 2 bits. Now I will begin with my always block. So we just have to write always at the red, and this is the sensitivity list. So inside this, we have to mention the input because output only changes because of the input. So we will mention all the inputs which affects this output y. So in our case, all these three inputs, A, B, and select, affects this output y. So I will write A, B, and select. So it basically means that this always block will only trigger when there is a change in this sensitivity list. So I will complete the always block. So I am modeling the behavioral model of a mux. So first I will give a condition. So when the value of this select line is 0, the output should get to A. And when the value of this select input is 1, the output will get B. So I will put on the conditions. So it's a very simple mux with two inputs. So I will go ahead and check for any compilation errors, whether I have made any typos. Okay, the code is just fine. So just to show the output, I will also write a small test bench. I will mention all the signals. I will mention the duty, and I will assign all the ports. Since the signals are of same name to that of duty, I am doing the wildcard assign. Now first I will write an initial block for $monitor that will continuously monitor any changes to the output Y. Then I will write another initial block in which I will provide stimulus to this duty. Right. Now I will assign some values to both the input signals. I will concatenate them and assign a 2-bit value. So the value of A will be 1 and the value of B will be 0. So next I will assign a value to select input or the select line. So for our first case I will assign a value of 0. Then I will wait for the next time slot and I will assign 1. So it is very simple. So when the when the select line will get 0, it will just take A. So we will get 1 in our case. And when the select line will be 1, it will take B and the output will be 0. So let's begin with the simulation. Okay, there are some errors, a typo, I should say. Just a second. I forgot to write B here for binary. Now it should work just fine. Yep, it worked. So let's go ahead and simulate the code. So as you can see right here, we are getting the expected outputs without any problem. So what is the demerit of generic always block? So the problem is that I have already discussed earlier that it does not declare the designer's intent. So right here, since we are modeling a mux, we know it that we are modeling a combination logic, but it does not inform whether it is modeling a combination logic or not. So which makes things a bit complicated. Suppose if we mistakenly implement somewhere in this always block, if we mistakenly implement some sequential logic or a latch logic, so the code will simulate just fine without any error, but it will cause problem or trouble during the synthesis. So this will cause a mismatch between the simulation and the synthesis. So suppose if I didn't write the else condition, so what will happen? It will just automatically infer a latch. So what will happen that whatever value is given to y, it will retain its value if the select input changes to 1. So in our case, the primary stimulus is for the select input is 0, which selects the value of a, and the value of a is 1. Since we haven't written any condition for the b input, changing the select line to 1 will not cause any change to the output. and it will retain its previous value, which will be 1 in our case. So let me go ahead and run the code. So as you can see right here that after changing the select from 0 to 1, the monitor block does not detect any change to Y. So it retains its previous value. So this is mostly because of the designers or coders error, and we might miss it. So to solve such kind of problem, SystemVerilog introduced a specialized block which tell us the designer intent, whether the designer want to implement a combination logic, a sequential logic, or a latch. So let me go ahead and change this to always com. Okay, so always com is a specialized system verilog block for combination logic that warns user if unwanted latch or non-combination logic is implemented. And also you can see right here that I am not writing any sensitivity list because there is no need of inputs inside sensitivity list as it automatically includes all the input from the block. The block always executes at simulation time 0. So just remember, it is very important. So suppose for our previous example, if it does not detect any change to its sensitivity list, then the block will not execute. In fact, we have to provide stimulus in such a way that the value changes so that the block can be executed. But the specialty with the always com is that it will always execute during simulation time 0 regardless of any changes with the input. So it gave us a lot of advantages. So here we have, let's run the code once with the else statement. Here we are completely satisfying all the conditions and it is a pure combination logic. So let's go ahead and run the code. So as you can see right here that it is running perfectly and we haven't mentioned any kind of sensitivity list, yet it still worked brilliantly. So what happened if I comment the else condition and thereby I inferred a latch? So what will happen since always com already mentions the designer intent that my particular procedural block is getting used for combination logic, and if there is a latch it will warn the synthesis tool or the checkers that the intended functionality is different. If suppose I'm using always com and inside that always com I have not mentioned a condition and it is not satisfying every condition, then a latch will be inferred. So the synthesis tool will warn about this unwanted behavior or the error in the coder's intent. So other than that, the other benefit is that the always com will always execute at simulation time 0. So let's move on to always latch. So always latch is used to model latch logic. It does not need to have any sensitivity list like always com, but at least one variable should not change inside its procedural block. And for this case, for y, at least one value should not update. Like at least one condition should not update. So to do that, I will just comment this, and by commenting this, it will, because since I am using always com right now, it will just infer a warning if we will use any synthesis tool or checker. But just to avoid the warning and just to make it clear that your intent is to model a latch logic, you just have to write latch, and this will just model the latch logic. It is that simple. So the only difference and only rule for latch logic is that one of the condition should not update. So it is that simple. So after that, let's go ahead with always FF, which is used to model sequential logic. And it all, like always com and always latch, it also clears the designer's intent to the simulator or to the synthesis tool or checkers. So there are certain rules for always block, is that there should be a sensitivity list, and every signal inside the sensitivity list must be qualified with either posH or negH. So, and after that, every assigning should be done using the non-blocking assignment. So I will go ahead and write a very simple code of a D flip-flop. So I will have an output Y and an input D and another signal which is clock. Finally reset. So to write an always FF block, you just have to write always, and like com and like latch, you will just write FF. But for this case, because sensitivity list is not automatically inferred, you have to mention the sensitivity list explicitly by writing at the rate. And inside the sensitivity list, you should mention the posH or negH, which basically mentions that whether this signal, whether the sensitivity list updates during the negative edge of this signal or the positive edge. So for my case, I want asynchronous reset D flip-flop, and the reset should trigger during the neg edge, and the clock should trigger during the pause edge. So I will mention pause edge of clock and the neg edge of the reset signal. So I will mention the condition. So if reset is low, The output will get here. Just remember, we will be using, since it is a sequential logic, we will be using uh, the non-blocking assignment, which I have already discussed during my video in which I have compared the non-blocking and blocking assignment. Else output will be assigned with the input. It is that simple. So I will go ahead and I will write a test module. So I will provide some stimulus. So remember, regardless of whatever the change is in D, it will not execute. It will only execute when it detects a change in clock and reset. So first I will go ahead and also create a clock signal. So let's say after every 5 ticks, the clock will change. So first I will apply the reset to be low. So when the reset is low, the Q will get 0. And I will do that for, let's say, 6 clock ticks. And I am doing this during the neggage of clock to avoid any race around condition. After this, I will turn the reset to be high. So in the next initial block, I will apply the stimulus. First, I will wait till the reset goes down. But I will also apply some stimulus right here. Check whether the reset is working or not. For that I will set t is equals to 0. And remember, I'm using neg h here just to avoid the race around condition between the clock signal and the input stimulus. And I will repeat that for 5 more times. For that only, I will apply 1. So first, let's check for any possible compilation error. Okay, there are no error. And I will also mention our dollar stop right here. Just a second, I need to make one more change since the clock signal is of logic data type. I will instead put it inside an initial block, and I will use forever, and the first value of clock should be 0. And then it will forever change from 0 to 1, then 1 to 0, and I will end the block. Now let's go ahead, compile the code to check for any compilation error. Okay, it worked just fine. So I will go ahead and simulate the code. Okay. Okay, as you can see right here that the code is working just fine. So our first stimulus was 1, but since on that time the reset was 0, the Q was only getting 0 because of the condition right here. And it's an active low reset. So when the reset is 0, the Q will get 0. And when the reset becomes 1, it detects the change, and only that it transfers the value from D to Q. But since the value of output Q was already 0 because of the reset, the monitor does not detect any change in its sensitivity list, and it does not trigger. But the value did get passed, technically or logically speaking. After that, the several clock ticks later, the value of D is changed to 1. And during that time, it detects another change at the postpone region, and it transferred that change to the output, as we can see right here. So that's all about the difference between always block and always com, always latch, and always FF. Thank you so much, and stay tuned for more. Thank you.